Hello again and welcome to another video. Now in the last video I showed you how to make a multicast TV server using a Raspberry Pi. Now multicast can be a problem on consumer grade equipment like you'd have at home, especially when you're using high bandwidth stuff like video, which is what obviously the TV server is. Now I'm going to show you in depth what actually happens with multicast and why it causes a problem on most people's home network. We'll just have a quick look at the amount of data we're talking about here. Now in my previous video on PID scanning and DVB snooping, we saw that there was roughly 23 megasecond for the whole transport stream. Now looking at the graph here of network traffic, we see roughly that's the same shown here as well, 23 megasecond. So I've had this on for 3 and a bit hours, and in that time it's sent 33 gig out of the network interface from that Raspberry Pi. So it's a significant amount of data. Now that's just a single DVB adapter, but if you had 5 of them and you're putting all the stations out on your network, then you're talking over 100 megasecond. So you've really got to take care not to send that out of all the ports of your switch. Okay, so what's actually in that traffic? Well, I've done a packet capture here of what comes out of that network interface of the Raspberry Pi there. Now the source address is just the IP address of the Raspberry Pi, but the destination address you can see is that first multicast group we set up. Now if we go down into the actual details here, it's the destination address that I'm interested in, and I'm showing it as bits down the bottom here. So this here, 0100-5E01010B, is represented by these bits here. Now that maps to the layer 3 multicast address that I gave it. So I'll show you on the board here how those two translate to each other. Now I'll start with the layer 3 multicast address that I gave it, and I'll spread it out a bit. So 239.1.1.11. Okay? Now if you take that 239.1.1.11 and look at that in binary, in just the bits, we get a stream that looks like this. We get 11101111. Next one is all 10001. Same again. 00000001. And 11 is 00001011. Okay, that's the binary representation of that layer 3 multicast address. Now if I go back to the packet capture and look at the destination address for that multicast group, I'll just write that out. Okay, so I'll write it underneath here. So we've got 01 00 5E. What have we got? 01 01 0B. Okay, now I'll write that out in binary bits as well, just to keep it all in order here. So that's 01 000 00001. All the zeros are 0000 0000. 5E 0101 1110. Now up to 01 here, which is pretty easy. 00000001. Same for the next one. 00000001. And the last one for 0B is 00001011. Okay, so there's the binary for both the layer 3 multicast group and the layer 2 frame that gets sent out onto the network. Okay, now the first half of any MAC address is the OUI, the Organizational Unique Identifier, which usually is the product vendor. But in this case, this one here means it's a multicast frame. So that is between there and there, okay? They're the first bits that relate to that. Now if we look at the remaining bits, you can see the similarities. We've got the same bits here for 11, 1 and 1. Okay, so what happens here though is this 0, that first 0 doesn't come into it. So it's sort of between there, if you like. Okay, they will all match the same bits from the layer 3 address. This bit here will always be 0 for a multicast frame. Even if that was a 1 up here, that would still be 0. So that's a 0. But the rest get mapped. Now if we go up to the top here, just to point that out, we know that in a multicast group, the first bits are always going to be 1110. So that leaves these 5 bits here that aren't represented on the MAC address. Okay, now there's 32 possibilities there, so that this particular layer 2 address could represent 32 different types of, 32 different layer 3 addresses. The way you get around that is, the chances are pretty slim for starters, but if there is a case where the frame gets forwarded to a host that didn't want it, it would check it once it gets to the layer 3 anyway, and then would discard it if it wasn't the right IP address. So that's how the layer 3 multicast address gets mapped to a layer 2 multicast address and gets sent out on the switch. Now if we go back to Wireshark and have a look at the packet capture again, you'll see that this destination address that ends in 11, you'll see, as I said, goes to 0B on the end, the .12 one, 0C, and so on, .13, 0D. And also remember that the MAC addresses aren't encrypted in wireless too, so if you see multicast frames in wireless, you can sort of work out what's going on in the network because the MAC address isn't encrypted. When I talk about a switch, most people probably have something like this, what they'd call a router at home. Now, when I say switch, what I'm referring to is you see these outputs here? That's part of a 4-port switch, and the wireless interface is also a part of that switch. So that's a switch. Now, to demonstrate this, I'm just going to use a switch only with 8 ports, okay? So this is just a switch without any other functions, just to show you how the broadcasts happen in real life. So I'll set that up now and show you. Okay, here's what I've got set up. I've got the Raspberry Pi's network connected into port 1 of the switch, and port 2 goes to this Linux laptop, and port 3 goes to this Apple laptop. Now, the port up here just goes up to my DHCP server so these hosts get an address, but that's not going to come into it really. So what I'll do, at the moment it's not running, but I'll start it and then we'll have a look at the on Wireshark on these 2 hosts, see what they do. So I'll just start it running, and what you'll see first of all is the lights on the switch will all start flashing. Okay, so that's multicast data coming from the Raspberry Pi pouring out into the network. Now these laptops don't have VLC running, they're just getting fed this data anyway, even though they didn't ask for it. So you can see here, I'll just stop this one, you can see all the multicast groups are coming in, so that's a whole 23 meg a second of bandwidth being chewed up for no reason, which is taxing on the switch and also the rest of the network in general. So it's what you want to avoid. The setup this time is the same 2 laptops and the Raspberry Pi, but instead of going into that dumb switch, they head up into an enterprise grade switch here. So this is a 48 port switch, but it can be aware of what multicast is and only forward it to the hosts that want it. So these 3 cables are just the Raspberry Pi and those 2 laptops. Okay, now I've got Wireshark running on both of these laptops doing the capture, and I'll just start DV Blast streaming the video now from the Raspberry Pi. So that starts up. Now the Raspberry Pi network light's flashing away, so it's feeding data into the switch. But as you can see on Wireshark on both of these devices, there's nothing coming in from the Raspberry Pi. Now if I go to the Linux one here and open a network stream of one of those streams, if I start playing that, okay, it starts playing and the data starts coming in, obviously, so I can play it. But still nothing on this laptop. That's because this laptop hasn't asked for it. Now, if I stop that, the traffic will stop coming in. Okay, so there's this thing called IGMP, Internet Group Management Protocol, and what that does in a switch that knows what that is, when it's fed all this multicast from the Raspberry Pi, it doesn't flood it to all the ports. Like the dumb switch did, it doesn't. Unless one of these hosts specifically asks for that multicast group. And if it does, it'll say, oh, okay, you want that multicast group, then it will flood it out of that port, but that port only. So, you know, the ones that haven't asked for it, they won't get it. So in this capture, if I look at just IGMP, somewhere when I started that stream, you can see this is where it left it, that's where it joined it. Okay, so from this device, .185, that'll be this laptop, it said it wanted group 239.1111, which is our TV station. So then the switch heard that. It keeps an ear out for IGMP. It's called IGMP snooping. Okay, so it hears that, it says, all right, this machine wanted it, so we'll send it out that port. And it was playing it until I stopped VLC, and then VLC would have passed up the chain, it said leave group, and then the switch also saw that, said, right, that port doesn't want it anymore, so we'll stop flooding it. And that's how it works. So this multicast TV server stuff, you really need a multicast capable network, otherwise you'll hit problems on a home network. Now, I will get into a way around this where we convert that to TCP, but it's no longer a multicast network at that point. But I'll do that in a future video and show you how you can run this as a TV server, just not multicast, at home, so you can use it on a non-enterprise network.